This is lecture 22 for Data Science 100 and Data Science 200. And the topic is principal components analysis. So we're going to look at how we can use the tools of linear algebra to decompose high-dimensional data. So this is the first lecture that we're going to have on unsupervised learning. And in the last lecture, you saw a more detailed look at the taxonomy of machine learning. So this lecture is going to be very linear algebra heavy, and I recommend that you refer to the linear algebra resources that we have on Piazza if necessary. So our agenda, we're going to start with the motivation for principal components analysis. Then we're going to introduce the singular value decomposition and the theory behind it. And we're going to define principal components and explore their properties and usefulness. So let's start with the motivation. So look at the data in this table. So we have height in inches, weight in kilograms, weight in pounds, and age. So if I ask you how many dimensions does this data have, what would you say? Well, if you just looked at the data directly, you might say, oh, there's 4 columns, so it would be 4 dimensions. But the 2 weight columns are actually redundant, right? Because weight in pounds is just roughly 2.2 times the weight in kilograms. So the real dimension count here is 3. So in linear algebra terms, we'd say that this matrix has a rank of 3. So more generally, we would say, when we think about the data set's dimensionality, it's going to be the rank of the matrix that represents that data. All right, now, throughout this class in lectures and labs and homeworks, we've used visualizations as a part of exploratory data analysis. And it works really well when we're looking at 2-dimensional data. But what happens when we want to look at data that has higher dimensionality? Well, it gets a lot more complicated. We could use things like maybe adding in hue or the size of points or some time dimension to try and show additional dimensions. But all of those, as you're going to see in just a moment, do a really poor job of trying to help us visualize the data. In particular, we're trying to discover insights about the data. And it can be very difficult to discover those insights if we just rely on techniques like hue, size, and so on. Now, if we want to explore the associations between 2 quantitative variables, the easiest thing that we typically do is just to do a scatter plot of those 2 variables. So if we had higher dimensional data, maybe what we could do is look at lots of different scatter plots as an approach. So let's look at a demonstration. So for this, we're going to go to our lecture code notebook, and we import in some libraries, and I'm not going to look at this data set. The data set I want to look at is this data set that gives the percentage of body fat, age, weight, height, and 10 body circumference measurements for 252 random men. Now, for this visualization here and exploration here, we're just going to use 8 of those data sets, 8 of those attributes rather, and so we'll just read those attributes in, and you can see we have percent fat, we have density, age, weight, height, neck, chest, and abdomen measurements. So now we could do a scatter plot of the fat versus density, and what we're going to see, this is density in grams per cubic centimeter, what we're going to see is that pretty much those 2 are completely redundant. Now it's not perfect. We get a near line, so there's a very strong correlation, but it's not a perfect correlation. We do have some of these that fall off of that line. Now let's look at instead the neck measurements and chest measurements, and here, the data is definitely 2-dimensional. This data, we could argue, is almost 1-dimensional, but this data here is clearly more of a scatter plot. We can see that there's a correlation, but the data is definitely not as tightly correlated as it was when we looked at the fat and density attributes. Now, what if we look at something like age and height? Well, here we can see that, as we increase the age, well, the height drops a little bit, which is to be expected because the spine curves as you age, and so you tend to see people losing height as they get older. But other than that, this is not a line, so it's definitely a 2-dimensional data set. Now, one thing to notice is that while most of the points lie in a range between 60 something and almost 80 inches, we do have this one person all the way down here who's 29.5 inches tall. And there are people who are very short, but it's going to be an extraordinarily small number of adult males who are less than 3 feet. And so, I think in this case, this observation might simply be an error. So we can actually look at this particular individual, and what we see is they're 44 years old, and their height is 29.5 inches. Their weight is 205 pounds. So that is definitely an error. So for someone to be 3 feet tall and be over 200 pounds, that's not a valid sample. And so we're going to drop that sample. And now let's repopulate our scatter plot. And what we can see is that this is really two-dimensional, right? There is not that strong it's not a nice tight correlation between age and height. It's pretty spread, which is what you'd expect. Okay, now let's say we want to look at more than 2 of these 8 attributes at a time. So what we could do is we could do a scatter plot where we're going to look at the neck, the chest, and then we're going to use, for density, we're going to use hue, and for size, and we're going to use size for percent fat. Okay. So now we get a plot like this. So here we have neck on the x-axis, and we have chest on the y-axis, and the sizes of the different dots represent the percentage of fat, and the density is different hues associated with each point. So looking at this, what can we say? Well, it looks like there is some relationship between the neck measurement and the chest measurement, right? There is some correlation there. But what about density versus fat? Take a look at that. Do we see a correlation between density and fat? Well, I'd argue that in this presentation, it's very hard to see that. But remember, we just looked at that, right? Here is density versus fat, and there is a very relatively tight linear correlation between the two. But when we go and look at it here, it's really hard to see that the sizes and the colors, the hues, are correlated. So while we can use hue and size to add more dimensions to a graph, it doesn't necessarily allow us to visually see those types of correlations that we might be looking for as a part of doing exploratory data analysis. So it's one thing we have to be careful with is, yes, we can plot it, and Seaborn lets you do all sorts of different plots, but do we actually learn anything from looking at that plot? And my argument here would be, for this, 4 dimensions, we can't really see anything beyond the 2 dimensions of neck and chest. Okay, now Seaborn does let you do things like plot all pairs. So we could take all pairs in our data frame that we've loaded, and we can plot all of those pairs. And here we have the plot of all of the different pairs. Now, this is kind of small, but here you can see this is percent fat here. And if we go all the way down, this is percent fat in the first column, then density. So as expected, the percent fat and density, so this is percent fat density here, this is density and percent fat here. This is what we saw before. We can see that there's a correlation. But we can also see correlations for percent fat with some of the other measurements. So like here, we can see a relatively, still it's 2-dimensional, but we can see that there's a correlation there, and that's abdomen. So that makes a lot of sense. Similarly with chest, there's a slightly weaker, let me scroll this up a little bit. There's a slightly weaker correlation Here, it's more of a scatter plot. Let's see what that column is. And that is height. So percent fat versus height, there's not a lot of correlation, and so on. So we could look at all of these and we can see all of the different relationships. So now we see that there is this very strong relationship between the percent of fat and the density. And so you might say, well, maybe the rank of this matrix is really 7 because of this relationship between percent fat and density. But if we ask our linear algebra command to tell us the rank of the matrix, it tells us the rank of the matrix is 8. Because these points are not exactly on a line. If they were exactly on a line, then it would tell us that the rank was 7. So we need something that's going to help us reduce the dimensionality of this data, because we can't visualize multiple attributes otherwise. And so that's what we're going to look at in the rest of this lecture.